Yes. Okay, so hello everybody, and this week we're very happy to have Kevin Zhang from Caltech, who'll be talking to us about EFT of dark matter direct detection. So, Kevin.
All right, thanks a lot for having me. It's my great pleasure to be here, and I'll be telling you about our recent work on the effective field theory of dark matter direct detection with collective excitation. So this is done in collaboration with my colleagues at Caltech, Tanner Trickle and Catherine Zurek. So let me start with a brief overview of the program toward LiDAR dark matter direct detection. So speaking of direct detection, perhaps the first thing to come to mind is a plot like this. So we have been making a lot of progress in conventional searches, which are mostly focused on the WIMP paradigm. These are based on nuclear recoils, and we're probing a lot of the parameter space of the WIMP nucleon cross-section versus WIMP mass, as we see here. This plot is already a little bit outdated, but it still serves to show the point. However, at lower masses, at GeV or below, we see that these experiments lose sensitivity very quickly. And the reason is quite intuitive to understand. Suppose we have a weak scale dark matter, 100 GeV. The mass is very similar to that of a target nucleus, say a xenon nucleus. So when it strikes the nucleus, we can detect the recoil signal. But if the dark matter is much lighter, say below GeV, it's striking a target nucleus, which is much heavier, so it just bounces back, and it's very difficult to detect a recoil signal. But of course, a natural set of ideas to go beyond nuclear recoils is to realize that in addition to the heavy nuclei, we also have the much lighter particles, the electrons in the target. So we can look for electron excitations. So instead of dark matter hitting on a xenon nucleus, it interacts with the xenon atom and can knock out an electron. And so we can detect this ionization signal. The associated energy scale is on the order of 10 electron volts, which is the atomic binding energy. And a related set of ideas is to use crystal targets, especially semiconductors. So basically, when we put the atoms together in a crystal, we have to talk about the electronic band structure instead of individual atomic orbitals. And we have the valence states, valence bands that are filled at 0 temperature. And there is a band gap, which is typically of order electron volts for semiconductors. And above that, there are conduction bands that are empty. So the cartoon here is that when the dark matter comes in, it can trigger a transition from a valence band to a conduction band. And then we can try to detect the subsequent ionization or scintillation signals. So this set of ideas has been extensively studied, especially in the last 10 years. And there are experiments, including Super CDMS, SENSA, and DAMIC that utilize electron excitations. And we're making a lot of progress on this. So to give you some numbers, so because we're sensitive to, well, suppose we're sensitive to energy depositions on the order of electron volts, and recall that the kinetic energy carried by the dark matter is about 10 to the minus 6 times the dark matter mass, because the velocity is 10 to the minus 3. So this means we can reach down to dark matter masses of order MeV. So we're pushing the reach significantly to the left in this plot. But of course, we can keep asking the same question. What if we want to detect even lighter dark matter? Below about an MeV, the dark matter doesn't even carry enough energy to trigger this transition event. So we cannot use typical semiconductors with a band gap of order electron volts. But of course, we can immediately ask, can we look for even smaller gap materials? And indeed, people have looked into those, including superconductors and Dirac materials. So these are very small gap materials with a band gap of order milli-electron volts. But these are somewhat futuristic in terms of experimental prospects. So we still want to explore new ideas for how to look for light dark matter if there's something that can be realized in the more near term. So this is what brought us to the idea of looking for collective excitations. So these are So perhaps the most familiar type of collective excitations are phonons in crystals. So these are the collective oscillation modes of the ions that are at sub-eV energies. So here I'm showing a cartoon. The dark matter comes in, instead of interacting with an individual nucleus or atom, it interacts with the entire crystal and can deposit a very small amount of energy and excite such a collective mode, which is a phonon mode. So this is something that has been studied relatively recently, including by myself. And on the theoretical side, we have carried out a pretty detailed study of many candidate target materials. And this is a plot from our paper back in 2019. So this is, here I'm patching this plot together with what I showed before for the WIMP searches. So we see that with these materials, which is a subset of materials we looked at, we can extend the reach down to about 10 keV, which is significantly beyond the regime of conventional searches. And also we can cover pretty much the parameter space above the neutrino floor. And there's also a detailed discussion on which material can perform better for what masses and what interactions I can find in this paper. So this allows us to basically have some guidance to as for what, for example, what target we should use for near future experiments.
Can I ask one question at this point?
Mm-hmm. Yeah,
maybe you will come to it, but what are relevant backgrounds in these kinds of experiments? You mentioned neutrinos already. Are there?
Oh yeah, definitely. Yeah, neutrino. There's definitely a neutrino floor, and so the other background. So there were a few of them. I guess there is a very recent study by Ruben Essig and collaborators, and they did a very good job on identifying some of the backgrounds from Cherenkov radiation and recombination, etc. So I mean, a lot of this is still, I would say, still being studied because it also depends a lot on the experimental setup. Actually, just on the next slide, I was about to talk about the experimental progress. Although, I guess, as I said, the background is still being studied. Yeah, we really want to make more progress in the coming years to mitigate the backgrounds in order to achieve better sensitivity.
Okay, thank you.
Yeah, thanks for the question. Yeah, so on the experimental side, there were also some very exciting news. The Tesseract dark matter project, which is based in Berkeley, is ongoing, and they're using a sapphire Al2O3 target and a gallium arsenide target, and they're designing ultra low threshold transition edge sensors, or TESs, to read out the phonons. So they're aiming for single phonon detection in the near future, which seems quite promising for this type of dark matter detection experiments.
So on that front, what kind of energy thresholds are they looking to achieve?
Yeah, so right now, the best they can achieve is probably on the order of several hundreds millieV, so just below an EV-ish. And in the next few years, I mean, at least from what they have been telling us, they're hoping to get down to a few tens of millieV. In the far future, we're hoping that perhaps even lower, that will be really advantageous because, I mean, if we have some targets with low energy phonons, and if we can read them out, that means we can extend the reach by quite a lot.
Okay, thanks.
Can you remind me, in the previous plot, on the previous slide, what energy threshold were you assuming for? Yeah,
so these curves are for the projected single phonon reach, assuming an energy threshold of 1 milli-electron volts. And if you increase that to 20 milli-electron volts, you get the dashed curves, and 100 milli-electron volts, the dotted curves. So of course, the reach will become worse for higher thresholds, and also not all of these materials will have a reach, just because some of them have phonons at lower energies and some have phonons at higher energies. But still, even with 100 millieV threshold, we can do a lot.
So just to check, is this a 1 kilogram year background free experiment?
Yeah, this is assuming 1 kilogram year background free, yeah.
Okay. Thanks.
I guess 1 kilogram year is perhaps the best we can do without hitting the neutrino floor, because with more exposure, I guess the neutrino background will become important.
So what on this plot is the 500 mil electron volt?
Good,
threshold?
Yeah. So I'm glossing over this, but this is showing the reach for nuclear recoils. So this is assuming we have a sensitive enough detector for the nuclear recoil searches. And so these basically extrapolate the curves on the right. Yeah, but the other curves are for single phonon excitations.
I see, thank you.
Yeah, and I guess in principle, there is a transition regime because, I mean, it should really be a smooth interpolation between nuclear recoils where the dark matter hits a single nucleus and the single phonon excitations where the dark matter interacts with the entire crystal. And in the intermediate regime, the important processes will be multi-phonon excitations, and those are actually numerically very challenging to compute. We're trying to make some progress on that, but still this is a work in progress. And on the other hand, you can try to use some models to deal with that. And there have been some recent works by Unicon and collaborators on that, which is also very interesting.
Once you get up to the once you get up to those energies, won't ionization type things start mattering as well? Well, you know, sort of band gap things. So it won't just be phonons; it'll be electronic excitations, right?
Oh yeah, good. So if the dark matter couples to electrons, then of course electron excitations will offer a complementary probe. And
so
actually, I'm going to show a plot in a few slides on exactly
so this is purely nucleophilic dark matter then for this plot.
Yeah, right. Yeah, for this plot, it's assuming just coupling to nucleons.
Okay. Yeah. Thanks.
All right. Any further questions? All right. So in addition to phonons, we can of course also look at other types of collective excitations. And the other set of ideas that we have looked into is to use magnons. So these are collective spin excitations in magnetically ordered materials. In the simplest case that are shown in this cartoon, we have a ferromagnet that everyone is familiar with. In the ground state, all the ionic spins are aligned. And when a dark matter comes in, if it interacts with these ionic spins, it can trigger a collective excitation mode, which is classically speaking a spin wave. And the quanta of spin waves are magnons. So magnon detection is like probably further into the future, especially if you're talking about single magnon detection compared to phonons, but still the theoretical calculation at least follows from a very similar framework. So we consider them together with the phonons. I should mention that magnons have also been discussed for axon detection, and there is an ongoing experiment, quarks, that use a very similar set of ideas, although the goal there is not to detect single magnons. So up to this point, what I've been showing is a two-dimensional parameter space, a cross-section or interaction strength versus the dark matter mass. But of course, there should be a third axis. So the interaction type, how the dark matter couples to the standard model particles. This plot that I just showed corresponds to a particular benchmark model where we assume that there is a heavy scalar mediator that couples the dark matter to the nucleon number. We can look at other models, say a dark photon mediator with kinetic mixing. And here we get a different set of curves for the predicted reach. And also the conclusion on which material will do better will also be different. And again, here, I guess I should briefly mention that we're doing a comparison study between single phonon reach versus the electron excitation reach, although it's a little bit hard to see perhaps on this slide. So these dashed curves are from single phonon excitations. The solid curves are from electron excitations. So they seem to have comparable reach above about 1 or 10 MeV, where we can have both. But of course, we can have many other slices in this parameter space because we really have a lot of interesting dark matter models to look at. And in fact, it may quickly get out of control because when we think about theories of dark matter, this is the picture that we have in mind. So there's just too much to be studied on a one-by-one basis. So that's why we want to have a common description at low energy to simplify things. And in fact, we do have a well-established framework for dealing with broad classes of dark matter models, which is an effective field theory framework. So for many of these models, we can match them onto a set of non-relativistic effective operators, which are well known from previous studies in nuclear recoils. So these are couplings between the effective couplings between the dark matter and standard model particles. So starting from here, we can forget about the dark matter models and just work with these effective operators. And so we want to establish an effective field theory framework for direct detection with phonons and magnons. And the first step, once we have these operators, would be compute the dark matter couplings to the lattice degrees of freedom because our target systems are crystal lattices. So intuitively, we can imagine that there should be a coupling to the particle number, namely how many protons, neutrons, or electrons are contained in each ion. There could also be coupling to the spin, coupling to the orbital angular momentum, or spin orbit coupling. So these turn out to be the leading order couplings that we can derive from our EFT calculation. And these are what we call crystal responses for a reason that will become clear in a moment. And then from these crystal responses, we can quantize the target system's degrees of freedom in the appropriate way to obtain the phonon and magnon modes and compute the excitation rates. So very briefly, as I will explain in detail a bit later in the talk, the dark matter, well, the phonon excitations can in principle be produced via dark matter couplings to any degrees of freedom of the ions, as long as you have the same coupling across the entire lattice. But for magnons, because first of all, these ionic spins come from electrons, not the nucleons. The nucleons are too heavy to contribute. The coupling has to be to the electrons. And also, in most cases, we need the coupling to the electron spin. And in more exotic cases, the coupling to the orbital angular momentum can also contribute. So all this I will explain in more detail later on. So if this reminds you of something, it must be the study, the pioneering study by Liam Fitzpatrick and others back in 2012. In their case, they looked at nuclear recoil calculations in the EFT framework. The situation there is quite similar. At the beginning, most of the focus was on the standard SI and SD interactions. But then starting with this work, they made a systematic extension of the calculation to the full set of EFT operators. And there, after obtaining the EFT operators, you compute the nuclear response functions and then compute the rates. So here it's very similar, although we're dealing with crystal response functions rather than nuclear response functions. But the overall strategy is exactly the same. So if you're familiar with that story, as we move on, it's useful to keep this analogy in mind. So there are 3 steps in this flowchart. So I'll start with the first step. The first step is to build the non-relativistic EFT. And as in any EFT applications, there is a bottom-up point of view and there is a top-down point of view. From the bottom-up,
so just before we move on, can I just ask a quick question? So
please.
In terms of the theories, like the theories of dark matter, that's like saying there are lots of things out there, but in terms of things that can give signatures in light dark matter detection experiments, for example, there was this study by Catherine and Simon Knappen and Tongyan Lin like a few years ago, looking at all the different kinds of models and finding that actually there weren't that many different kinds of models which were viable through other constraints and could also like give detectable rates in direct detection experiments. So in some sense, the space of models that might actually give you signatures is not necessarily that big. I don't know, that this is a more philosophical question. What is there a response to that?
Yeah, I mean, I totally agree with you on that. But of course, I mean, you can always argue that many of the constraints are model dependent, and I mean, they have various levels of, robustness. And if I just write down, say, a higher dimensional operator in the relativistic theory, and there's always the question of what UV completes this effective theory, right? And then,
well, maybe to sharpen the question up a bit. I guess is this EFT analysis going to point you to sort of stuff that you wouldn't have considered otherwise? Like just from looking at the sort of like the few canonical models, is there some sort of other examples of things which this sort of shows up that you wouldn't have thought about if you'd just been thinking about like those canonical models?
Yeah, well, I guess I'll later on in this talk, I will give a few examples, especially focused on the multipole models where you have a dark photon mediator, but the dark matter couples via a higher dimensional operator. I mean, that's one of the examples that will fit into what I just said. You have to talk about the UV completion to work out the other constraints, which of course will be model dependent.
Okay.
I mean, for this exercise, I guess the idea is more of, these brilliant proposals for detecting light dark matter using collective excitations and also with small gap materials that other people have studied. Most of the studies were carried out in very specific models, like just as in the nuclear recoil searches, spin independent and spin dependent, and here is like the dark photon mediator coupling to charge, or simple scalar mediators. But really, the theory space is supposed to be much larger, and we want to know for general theories how to do the calculation. So that's the main motivation for this.
Okay. No, that sounds good. Thanks.
Yeah, thanks for asking. All right, so from the bottom up, we can build up the EFT from the IR degrees of freedom. And here in the current case, we have the spin operators for the dark matter and the standard model particle, which can be the proton, neutron, or electron, which will be collectively denoted by psi in what follows. We have these momentum operators as well. But we have to keep in mind that there are two constraints on the form momentum from momentum conservation and Galilean invariance. So this reduces the independent kinematic variables to two, which are usually chosen to be the momentum transfer Q and this parameter called V perp. This is the component of the relative velocity perpendicular to Q. So we're gonna use this set of IR degrees of freedom to build up the operators. But of course, the procedure is already well known from previous studies from Fitzpatrick and others in the previous literature. And here I'm just repeating the list of operators. But conveniently, we can put them into different categories depending on whether the operator is a coupling to charge or a coupling to spin on the standard model side. And also whether it depends on the relative velocity. So there are 4 categories based on these criteria. And this will turn out to be convenient because as we'll see shortly, operators in each category, operators in the same category generate the same crystal responses, and operators in different category generate different crystal responses. So from the complementary top-down point of view, the idea is to start from a UV theory and take the non-relativistic limit. And for example, here I'm showing a list of options for coupling a spin 1/2 fermion dark matter to a mediator, which then can couple to the fermions in the standard model. So there are several coupling types that we can enumerate. For scalar mediator, we can have a scalar or pseudoscalar coupling. For vector mediator, we can have a vector or axial vector coupling at the normalizable level. But we can as well just write down higher dimensional operators. For example, at the next order, we have the electric dipole and magnetic dipole moment. And at the dimension 6 level, we have the antipole moment. And these are all the possible types of interactions, and other operators will just be these existing types multiplied by a momentum dependent form factor. And for each of these, we can take the non-relativistic limit of the effective current, and we see that the building blocks of the EFT operators will naturally emerge from this exercise. So in the end, the part of the EFT that we're interested in will be the 4-point operators coupling a pair of dark matter particles to a pair of standard model fermions. And for each model, we can derive the coefficient Ci in front of the operators that you saw on the previous slide. So to make it more concrete, let me give you a few examples. So we're gonna look at a dark photon mediator. The coupling to the standard model is to the electromagnetic current. This can arise from kinetic mixing with the between the dark photon and the photon. On the dark matter side, we can consider several possibilities. The simplest one is that the dark matter is minimally coupled to the dark photon, and this is essentially the Miller-charged model or the standard spin independent interaction. And here, just O1, this first operator, is generated at leading order. But there are other possibilities. For example, we can have an electric dipole coupling between the dark matter and the dark photon. And here, as we work out the non-relativistic matching, we see that it's a different operator, O11, that's generated. And similarly, we can allow the dark matter to have a magnetic dipole moment under the dark photon. And also, in this case, we have different operators generated. And in fact, there are 4 operators generated at leading order, and they fall into different categories. And finally, for an antipole coupling, we also have operators in different categories generated at leading order. So the calculation, the procedure for doing this calculation is pretty clear, and I will talk more about these models later as we discuss the detection rates. So that's the first part of the story. This part is pretty much already developed in the previous literature. So here I'm just reviewing the key results for completeness. And then moving on to the second part, this is the part starting from which we're gonna specialize to the case of crystal targets. So the goal is to match these effective operators onto the lattice degrees of freedom. So we have been looking at operators coupling a pair of dark matter fields to a pair of standard model particle fields. But what really happens in our experiment will be that the dark matter comes in, it can mediate a transition from an initial state to a final state in the crystal lattice, and then it goes out. So we need to find the matching between these two pictures. So the matching is provided by the Fermi's golden rule, which basically says that we need to evaluate the matrix element between the effective lattice potential, the Fourier transform of the lattice potential, which can also depend on the relative velocity. And here, there's also an energy conserving delta function involving this quantity omega q defined here. As I said, we're interested in crystal lattices. So for periodic lattice, we can generically write the potential as a sum over contributions from the lattice sites or over all the ions in the lattice. So here, L labels the primitive cells, which are the repeating units in this crystal lattice. And in each cell, we use J to label the ions. So we just sum up their contributions. And to take the Fourier transform, we see again that it's a sum over the ions, and each of them is accompanied by a phase factor. So the key quantity to compute is therefore the dark matter ion scattering potential. Once we have those, we can just add them up and then compute the matrix elements, and that will be the goal of the next step. So for step 2, we first want to compute this dark matter ion scattering potential, and we want to do this calculation in the non-relativistic EFT, just using these operators without reference to dark matter models. Because the calculation is very similar for the operators in the same category, I'm just going to pick one from each category. So we can write the effective potential as a sum over the contributions from the ions constituent particles. So alpha here runs over the protons, neutrons, and electrons containing an ion. And in each term, we have the corresponding phase factor depending on the position operator of these constituent particles. So generically, if we just want to evaluate these expectation values, it will be really complicated because we have to put in the wave functions for the nucleons or electrons and sum over all of them. But in our case, we actually have a very important simplification because we're interested in light dark matter. And here below about 10 MeV in the dark matter mass, the momentum transfer is always small compared to the inverse ionic radius. So we can make an expansion in the long wavelength limit and just keep the leading non-vanishing piece. And that's what we're...
Sorry, I just had to go away from my computer for a minute, so I think I might have missed something. Could you go to the previous slide? So how you're setting things up. Okay, so you're setting things up with this scattering potential thing.
Yeah.
Right, okay. Okay, and so then you have the EF and the I for the energies of the collective mode.
Right. Yeah. So, yeah, how to compute this matrix element will be discussed in the next step, step 3. But right. Here, we're just working out this quantity between for the coupling between the dark matter and the ions in the crystal.
Okay. Thanks.
All right, so let's move on. As I said, we want to make an expansion in the long wavelength limit. For 2 of the operators that do not involve the relative velocity, the calculation is very straightforward because we can just keep the leading order piece and set these phase factors to 1. And what we get will be the sum over identity operators and sum over spin operators. And so these will just give us the total particle number and the total spin respectively. For the other 2 operators, because there is a velocity dependence, we have to be more careful. If we write out the velocity, this V-perp operator, in terms of a center mass piece and a piece that acts on the wave functions, the first 2 terms here will not act on the wave functions, so we can treat them in the same way as in the previous 2 operators, namely setting these phase factors to 1 and obtain the total particle number and the total spin. The last term here is an operator that acts on the wave functions. And in fact, it is the probability current operator. So essentially the leading order piece will vanish because of probability conservation. So we have to keep the next leading order piece IQ.x alpha. And once we do that, we can carry out some algebra to show that in the end, is the orbital angular momentum operator that emerges. So as we put things together, these two operators will give rise to a combination of couplings to the particle number and orbital angular momentum, and the spin and the spin orbit coupling, respectively. Yeah, this is pretty much what I just said. Okay, so we can carry out the same exercise for the full list of operators, and the final result is presented in this long equation in the box over here. And we can see several generic features on the result of this calculation. So first of all, every operator will give rise to either a coupling to the particle number or a coupling to the spin, the total spin. And in addition, for the velocity-dependent operators, we also get a coupling to the orbital angular momentum or spin orbit coupling. And so these quantities are what we refer to as crystal responses because they play a very similar role as nuclear responses in the Fitzpatrick et al. Calculation. So just as in their work, we refer to the couplings to the particle number and spins as point-like responses because these do not involve the internal degrees of freedom of the ion. And for the coupling to L and the spin orbit coupling, these are the composite responses because the coupling involves the wave functions of the constituent particles. So in this way, as we put these operators into these four categories, it's pretty clear which operator generates which response. And that's also reflected by the equation on the left here. So that completes the second part of the calculation. And finally, we're going to move on to the part that involves the collective excitations. So in the third part, we will no longer make any, we won't make any more EFT expansions and just compute everything numerically. So, I mean, generically, if you're looking at only the very low energy excitations, it could be possible that you can further establish an EFT for the collective excitations, but we're not going to do that here because we're interested in the full spectrum of the phonons or magnons. So this will be a technical calculation involving a lot of the material details. So let me first sketch the big picture for what will go into the calculation. There are four types of responses that I just described. First of all four of them can in principle excite phonons. And this is basically because any coupling can shake the lattice. But there is a necessary condition, which is that the coupling has to be in a sense coherent to excite phonons. What this means is that the coupling has to be the same across the entire lattice. To be more precise, for the scalar couplings, for the couplings to particle number and L dot S, these are the scalar quantities associated with the ions. These couplings are trivially coherent in the sense that we have between one primitive cell and the next one, we have the same type of ions. So how many protons, neutrons, and electrons are contained in the ion is the same. And also L dot S will be the same because these are scalar quantities. But if we have vector or tensor couplings, these are generically not coherent. For example, if we couple to the spin, and if they're not ordered, then the vector will be pointing in random directions from one cell to the other. So we do not have a coherent coupling across the entire lattice. And in that case, it cannot excite phonons. But of course, the exception is where these vector quantities are ordered, and this can happen either spontaneously, say via magnetic ordering, or by applying external fields. So for magnons, recall that those are excitations involving the magnetic ions spins. So we need to couple to these ion spins. First of all, as I already mentioned in the introduction part of the talk, the ionic spins come only from electrons. And in many cases, these are just a total electronic spin. So we need a coupling to the spin of the electron. In other cases, we may also have the orbital moments contributing to the magnetic order. And in those cases, the coupling to the electron's orbital angular momentum can also contribute to magnon excitation. And I will give a concrete example of that in a few slides. So the upshot is, again, as we go back to Fermi's golden rule, we need to compute the matrix element.
Just to come back to that thing. So in the previous place where you wrote out the Fermi's golden rule, you had it between states of definite energy. But in a material, like your phonons and things may not be like a single pole with a very definite energy. They might be things with some damping, there'll be some complicated spread out thing. How do you deal with that?
So phonons are quasi-particles, right? Just as in quantum field theory in the vacuum. I mean, of course, if a particle is unstable.
Yeah, it's not stable, and they generally won't be stable, right?
Right, so for the, they're not stable because there are phonon self-interactions, right?
Yeah.
Yeah, but those are still well-defined quasi-particles in the sense that the width is always much less than its energy.
And that'll be, yeah. Is that true in all the cases you care about? It's true in some cases. Like, I remember seeing some plots of these things, and it looks like a pretty complicated forest where things merge together in some cases. Is that always true?
I guess at least for the crystal targets that we look at, and especially those used in the experiment, like gallium arsenide or sapphire, these have very well-defined phonon quasi-particle modes. These are really sharp peaks if you look at the
things spectrum. Like that, yes, sure.
Yeah. I mean, in other systems, it could be more like a continuum. And as you said, we have to be more careful about the treatment of these states. But that's not a problem in our calculation.
Okay, thanks.
All right, so we want to compute the matrix element between the ground state, which we assume the system is prepared in, and a single phonon or magnon state, which is labeled by a branch nu and the momentum k. So once we plug in the expression for the total scattering potential as a sum over the ions, so we see that this quantity that we just computed in the previous step will enter this equation. And then the calculation, how the calculation proceeds depends on whether we're looking at phonons or magnons or some other excitations. For phonons, because these are oscillation modes of the vibrational modes of the ions, we have to quantize the position operators of the ions. And the leading dependence on the position operators is from this prefactor, this phase. And so we just do the standard quantization procedure and would plug in this equation and obtain the matrix element. But of course, the difficult part or the non-trivial part of the calculation is to find the canonical phonon modes. And that involves a diagonalization calculation. And that's the part that we use first principles numerical calculation to deal with. So this is done with density functional theory, which is a set of well-established tools for material science calculations. And a lot of our calculations rely upon the DFT work in collaboration with a group led by Sinead Griffin at Berkeley Lab. So they were able to compute the crystal Hamiltonian in a very reliable way. And we then use that information to solve for the phonon eigenmodes using the PhonoPy program, which is a widely used open source program. So in the end, the rate formula will look like this. So there are several important ingredients that are worth highlighting. The last factor here is where the dark matter coupling enters. So this is essentially the same as the equation that you see on the background. These contain the operator coefficients, and together with these ionic quantities, and those are target specific. So for the rest of the equation, we have a sum over phonon branches, a sum over the ion amplitudes, the phonon eigenenergies and eigenvectors that we compute numerically enter in the expected places. And finally, it's worth noting that in the denominator, we essentially have something that resembles the harmonic oscillator. So yeah, that's the story for phonons. For magnons, because we have to look at the terms that are that involve the coupling to the electronic spin or orbital angular momentum. We just circle these terms in this equation, but these are not directly the ionic spins. So we have to make a projection onto the ionic spin operators. So this is a material specific calculation that requires understanding the origin of the magnetic order. But that the result of that calculation is essentially two numbers for each ion, showing how much of the ionic spin comes from the electrons and come from the spins of the electrons, and how much of the ionic spin comes from the orbital moments. So these are the lambda s and lambda l parameters. And once we have that, we can write everything in terms of the couplings to the ionic spins. And then we expand the ionic spin operators in the Huston-Primakov bosons and work out the diagonalization for the spin Hamiltonian. And again, we have to first use either experiment or DFT calculations to figure out the spin Hamiltonian, and then carry out a diagonalization calculation to find the eigenmodes. And the rate formula looks very similar to the case of phonons. Again, there is this factor that contains the dark matter physics. These are essentially what you see in the background, but just extracting the coefficients of the couplings to S and L. So again, there is a sum over branches, sum over the ion amplitudes, and these U and V matrices are the rotation matrices to the magnon eigenmodes. So they play the role of the phonon eigenvectors, but this is for the magnon case. And special to the magnon case is that we have to have a vector that we call R that captures the magnetic order. Once we put everything together, we can just compute the rate for any effective operator. So that completes the final step of this framework. And in the last few minutes, I'll go back to the examples and show you some plots. So the examples that we looked at earlier in this talk are the dark photon mediator models. We talked about 4 models: the spin independent, the electric dipole, magnetic dipole, and anapole models. So we have already worked out the coefficients of the non-relativistic effective operators. And now we can plug these into this master equation for the effective scattering potential. But of course, we first need to find out the terms that are generated. So for the SI and electric dipole models, we see that these terms involve just the coupling to the particle number. So these can give rise to phonon excitation, but not magnon excitation. Also, we can notice that the C11 is accompanied by 1 power of the momentum transfer. So we expect the rate to be correspondingly suppressed. For the other 2 models, we see there are more operators generated. So we have to look at more terms in this equation. And in addition to the coupling to the particle number, we also have couplings to S and L, which means that these can drive magnon excitations. And again, we can look at the power counting and notice that the anapole model is higher order compared to the magnetic dipole model. And also comparing the first two models and the last 2 models, we see that there is a Q² suppression going from the first 2 to the last 2. So all these power counting arguments will translate into a hierarchy in the projected sensitivity. So this is showing the reach that we computed again, assuming kilogram year exposure and no background. And we see that indeed, the SI interaction we are most sensitive to because it's not suppressed by the momentum transfer or the velocity. And then for the other three models, we get successively higher order in Q. So the reach becomes lower. The reach becomes weaker accordingly. And we can make a parametric estimate for the rates, but in the interest of time, I'll skip this part. I should mention that for the targets we consider, gallium arsenide and silicon dioxide, also known as alpha quartz. So these have complementary features. As you can see, the crystal structures are very different, and also the phonon dispersions look very different. There are many more phonon modes in quartz, just because there are more ions per primitive cell, so there are more degrees of freedom. And also the energies are quite different. This is, in gallium arsenide, it's up to about 35 millieV. In quartz, the phonon energies are up to 150 millieV.
So just to ask here, is this the old calculation for SiO2?
This is the new calculation.
Oh, so it's still significantly below.
I think
it's still significantly below gallium arsenide.
Yeah, I think so. Yeah.
Okay, that's interesting. It'd be interesting to compare to that.
Oh yeah. So I mean, it will not. Yeah. So I guess this is from the context is a private conversation with Robert a while ago, which is that we actually made some errors in the 2019 paper where we compared a large set of target materials, and for silicon dioxide, the error led to a stronger reach. But once we corrected that, we find it's still one of the best, although it's not a significant better than some of the others. But compared to gallium arsenide, it's still better.
Oh yeah, I guess I was thinking of sapphire or something. Compared to gallium arsenide, maybe this is about right. Okay, thanks.
Yeah. So gallium arsenide is one of the targets used in the SPICE experiment, which is part of the Tesseract project, as I mentioned before. Quartz, I mean, even after correcting for this small error, we still find it to be one of the best targets. So this is something we would recommend for future experiments, especially because it can also be synthesized relatively easily compared to some of the other materials we considered. But one thing to notice is that these targets do not have S or L order, which means that phonon excitations proceed only via the end response, namely couplings to the particle numbers. But two of the models, the magnetic dipole and anapole models, also generate couplings to S and L, and we want to probe these couplings as well. So these are best probed by magnons. So on this slide, we zoom in onto the magnetic dipole and anapole models. The gallium arsenide and quartz curves are the same as what you saw before. These are from phonon excitations. The other curves are from magnon excitations. So YIG is yttrium iron garnet, which is perhaps the best studied ferromagnetic material. It's described by a Heisenberg model that involves only the spins of the electrons, but not the orbital moments. This is the material used in the CRAX experiment for axion detection. So this is something that people know how to synthesize in good quality. The other target that we looked at is more speculative, alpha ruthenium trichloride. This is one of the so-called Kitev materials. And the interesting feature is that there's a bond directional coupling. So what this means is that this is really, this is a three-dimensional material, but it has a layered structure. In each layer is a honeycomb lattice, as you see here. But the three types of bonds are different. So along a red bond, the spins, the ionic spins interact only via their X component. And similarly for the green and blue bonds, and these are referred to as X, Y, and Z bonds respectively. And because of this very special feature of the couplings, there is a lot of interesting phenomena on the condensed matter side that has been studied pretty extensively in recent years. But from our point of view, we're interested in dark matter detection, especially light dark matter detection. Our focus point is kind of different from the condensed matter people. And essentially, there are two nice features of this material that drew our attention. One is that the order, which is anti-ferromagnetic, involves not only S, but also L. So these are the so-called spin orbit entangled moments. So this will be sensitive also to dark matter couplings to the orbital moments. And the other nice feature is that the gap magnon modes are at very low energies, below about 10 millieV. So assuming we can achieve this kind of low threshold, we can really extend the reach to very low mass dark matter compared to all the other targets. So this is really nice. But again, this is a very speculative. This is something that has not really been discussed in the context of detector, making a detector. But I guess the idea here is to highlight the features that make this material advantageous, and hopefully, if we can find something else that also has these features but are easier, but is easier to synthesize, there'll be a very good candidate for a near future experiment. So again, we can make parametric estimates, and in the interest of time, I'll skip the details. But the end result is that we can show the magnon reach is parametrically better. However, we can see from the plot that quartz is actually not too far behind. That's a little bit worse than the magnon targets, but not by too much, especially for the higher masses. So this is encouraging news because phonon experiments are much more mature. So we can really hope to probe a lot of the parameter space into these models already with the phonon experiments in the near future. So I guess I'm running out of time, so let me conclude. So the take-home messages are: first, collective excitations such as phonons and magnons offer a novel path to detect light dark matter. On the experiment side, there are new experiments such as SPICE, which is part of Tesseract, that are moving forward. And we're really hoping to hear more from them in the next few years. On the theory side, we have been studying the calculation of the detection rate, especially in the effective field theory framework. And now with our recent work, the theory framework is already set up for computing the rate for general dark matter models. So I'll end here with the summary slide for our EFT calculation, or these 3 steps. And we have the theory framework ready for making predictions for general dark matter models. So yeah, thank you very much. And I'll take further questions if there's any.
Okay, yeah, thank you very much for a nice talk. Let me